Yay! Welcome back to lesson 5.3. My friends. You guys with us? Yeah. All right, we're talking about polynomial functions. Some key vocab words of like degree, standard form, leading coefficient. We kind of broke that down yesterday a little bit. We'll talk more about that today. And then we're going through our common types of polynomial functions, and we finished off with the ones that like you're familiar with. Linear you do a lot with in Algebra 1, and quadratics we did a lot in Chapter 4 and Algebra 2. Okay, so the next highest degree, degree 3, looks something like this. If my largest power on the variable is a 3. Now, folks, this doesn't mean I have to have like all 4 terms. Like I could have something just like this, and that would still be classified as like a degree 3 polynomial function, even if you only have 2 terms. Any guesses what these are called? No.
Something tri?
Oh, good guess, but no. Trinomial means we have 3 terms. Good guess. Starts with a C.
What?
Think of when you have a power of 3. Cubic. Cubic. All right. And then the next one we're going to look at is 4. And these do, I mean, you could go all the way up to like degree 3027 if you want. Like these.
What does a cubic one look like?
Oh,
is it a square?
It looks something like this.
It's not cubic. Oh, I've seen that.
Yeah, we're gonna graph it. No, it doesn't look like a cube. Sorry. Degree 4. Maybe I have something like this: negative x to the 4th. Notice I'm writing these all in standard form, meaning the order of my powers is descending from left to right. Okay, degree 4. Any guesses what these are called? Quad does mean 4, but quadratic is 2. Good guess though. It does start with a Q.
What?
No.
Quadrant?
No.
Quadic?
Think there's 4 of these in a gallon.
Quart.
Quartic.
I know it.
Okay. These kind of look something like this. Like a W through Willis. 5, I think we call quintic. You know, if people have like 5 babies at once, we call them quintuplets. And it goes on from there, but these are really the only ones you need.
Wesley's a
familiar with.
quintuplet. Yeah, I am.
Okay. So let's try an example problem here. It says, state the degree and the leading coefficient of each polynomial in one variable. These technically aren't functions. We don't have f of x equals in front of them or y equals in front of them. If it is not a polynomial in one variable, explain why. All right, so first thing you have to check, these are 3 separate problems. This is number 1. The first thing you got to check is, do I only have one variable in this polynomial? Yes, what's my variable?
X.
Good. We have one variable. It's x. That's kind of like your first criteria in order for it to be a polynomial. Second thing, are my exponents positive integers, meaning whole numbers?
Yes.
Okay, we're good. There's no negative exponents. There's no fraction. Are all my coefficients real numbers? Do you see any eyes?
Yeah.
Okay. Yeah, they are real numbers, no eyes. So this one is a polynomial. Is it written in standard form?
Yeah.
Yes, it is. My largest power term is first, descending order from left to right. Notice how I don't have an x squared or an x term. That's okay. It's still a polynomial. So what degree is this, folks?
5.
5. This is degree 5, and I get that from looking at my largest power.
Same temperature outside.
That's kind of funny, actually. But it's actually 10 degrees outside. So,
Oh.
but that was a
Oh,
joke.
wind chills.
I appreciate the pun there. I do like that. Okay. Leading coefficient is the number in front of the first term in standard form. So if this is also 5 coming from this 5. Okay. All right. Number 2. is this polynomial?
No.
No, why not?
Two variables.
Yeah.
Not in one variable. Good. Two variables. A and B. So not a polynomial. Meaning we can't state the degree. It doesn't have any of that criteria. It's not a polynomial. Good. All right. Everything in one variable.
Yeah.
Check. One variable. I just have x. Usually it's x because we, like I said, we're gonna do these as functions. So usually we write function in terms of x. Oops. Is it written in standard form?
No.
All right. Let's rewrite it in standard form. Which term would come first?
Negative 8x6.
Good. Negative 8x to the 6th. Then
3x.
3x to the 5th. Good. You can cross them off as you want. Then 2x squared. Constant always last. Good. So you want to make sure you write it in standard form. That'll help you state the degree. Degree what?
6.
6. Good. Degree 6. LC? Negative 8. Good. So sometimes people make the mistake of trying to tell me what the leading coefficient is by looking at the polynomial not in standard form. They're like, oh, it's just the first number. It's 3. Okay, it has to be in standard form. All right, good on that vocab? It's not too hard. It's just different. Okay. All right, some notation with polynomial functions. You've seen this notation before. So here I'm given two different polynomial functions. B of x is a degree 2. What type would this be? How do I classify it? It'd be a quadratic. Yep,
Yes.
degree 2. It's quadratic. Good. C of x is a degree 3. What type would that be? Cubic. So I have a cubic function and I have a quadratic function. I'm going to keep throwing vocab at you. If I want to find b of 2, that doesn't say b times 2. How I read that out loud is b of 2. And parentheses in math can be confusing because we use them actually in a lot of different contexts. In our lesson tomorrow, we're going to use them for something else. That doesn't mean like times also. So just be careful. I would read this as b of 2. And what that means, if you look here at this notation, b of 2 means I'm going to plug 2 in for x into my b of x function, right? That's what that means. So I'm going to take out the x's, and I'm going to plug in 2. Everybody agree that's what b of 2 would mean?
Yeah.
Okay, let's do this in our head quick. We have 4 times 2 is 8 plus 1, we get 9. That'd be my final answer. B of 2 is 9. When I plug in 2, I get out 9. Okay. C of 1. This first letter is telling me which function it wants me to plug it into. So I'm going to use C of x. And whatever's in the parentheses, that's what I'm plugging in for x. Okay, so if I want to find C of 1, C of 1 is how I'd read that out loud. I would do negative, take out the x's and replace them with parentheses. Please, 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 please use parentheses. Getting good habits right now. All right, just like I did here, plug it in 1. So then plug in 1 for all the x's. Okay, let's go through order of operations here, because this was like the very first problem on the semester exam that some of you guys got wrong, because you didn't do your order of operations correctly. Exponents first. What's 1 cubed?
1.
What's 1 times negative 1?
Negative 1.
Plus 2.
1.
C of 1 is 1. Okay, last one. C of negative 1. Which function am I going to use? The red or the green?
Green.
The green. I'm using C. The only difference here is now I'm plugging in negative 1. Okay, this is going to give us a different answer. Start within the parentheses first. What's negative 1 times itself 3 times?
Negative 1.
What's negative 1 times negative 1?
1.
Positive 1 plus 2?
3.
3. Okay, that can be tricky. Be careful with your parentheses. All right, so we've done that before. Maybe you haven't done it with something like a degree 3 polynomial function, but you guys know how to evaluate larger powers than that. Yes, sir?
Could that also be a quartic one too? Because you're multiplying -1 times -1 cubed.
Oh,
Technically be written as
I see what you're
-1
thinking.
times 4.
In order to like classify it, it would need variables. So technically, like, couldn't classify something like this as a polynomial. Yeah, good question. All right, it's gonna get a little bit harder. I'm gonna start throwing in variables instead of numbers. Okay, so same functions here, b and c, but this says find, how I read that out loud is b of a. It's not b times a, find b of a. So all that means, same idea, folks. I'm going to use my b of x function. And here I have a letter instead of a number, but I'm going to do the same thing. I'm just going to plug that in for all the x's. So this is what I like to do. I like to set up a little template for myself by taking out all the x's and replace them with parentheses. And then whatever is inside of here, you're just plugging in for x. All right, so here I would do a squared, which is a squared, times 2. I get 2a squared plus a minus 1. I can't add those together. They're not like terms. That'd be my answer. So I get out, so something like this I could classify as a function. I get out something with variables and just not a number. Have you guys done that before, where you like plug in something other than numbers? I don't know if you have, to be honest. I don't know if you do this in algebra. I used to do it in algebra 1, I think, last year, but okay, let's try a little bit harder one. Find, how would I read this out loud?
C of n plus 1.
C of n plus 1. So the first letter right here is telling me which function to use. I want to use c, and in the parentheses is what I'm plugging in. So c of n plus 1. So set up that template for yourself. Don't forget about the negative. And then whatever in the parentheses, that's what I'm plugging in for all the x's. Now in this case, there's only one x. So that would be how I plug it in, and now I have to evaluate this. Oh boy, folks. N plus 1 cubed. Nice. You gotta multiply this out. Okay, I still have this negative 1 out here. You can change it like this if you want. Negative 1 times that. Okay, so this plus 2, but right now I'm just working this. Because that is my PEMDAs. I got to take care of that exponent first. Okay, so I'm going to multiply these two together. I'm going to do this in one step. N squared plus 1n plus 1n would be plus 2n plus 1. Okay, everybody with me? Now I'm going to have to distribute in that next n plus 1. So distributing the n, I get n cubed plus 2n squared plus n. Distributing the 1, n squared plus 2n plus 1. Okay, we can clean it up a little bit. I have some like terms here. N cubed, 2n squared and 1n squared would be 3n squared. N and 2n would be 3n plus 1. Oofta! I'm not done. What would I do next? Order of operations. What would I do next? Multiply in that negative 1. Good. Distribute that negative 1. That's really easy to do. It's just going to make all your terms negative. Negative n cubed minus 3n squared minus 3n minus 1. And then the last step, do I have any like terms? Just this little one right here. So I get negative n cubed. Notice how my answer I'm writing in standard form. Plus 1. And that is what C of n plus 1 evaluates to. Oofta! That was a little more algebra than thought it was going to be by just looking at it. Okay, makes sense? The notation? We're going to try one harder one. Holy letters. Holy algebra. Anyone want to try to read that out loud?
Well, grading can.
The directions. How do I read this out loud?
B of 2a minus 1 minus 3c times a squared.
Close. You read this part wrong. Minus 3 times c of a squared. So, let's take it piece by piece.
Oh, you have to subtract.
Yeah. Okay, let's do this part first. B, the number outside tells you which function to use, right? B of 2a minus 1. Let's just tackle that piece first. And then I'll take care of this one. Minus 3c of a squared. That's how I read that out loud. Okay. I'll use my highlighter here. Starting with b of 2a minus 1. Use my b. Let's do the template. What would I plug into all those sets of parentheses? B. Nope. B tells me which function I'm using.
2a minus 1.
2a minus 1. What's in the parentheses? That's what we're plugging in. Two a minus 1. The first letter tells me what function I'm using. The parentheses tell me what to plug in. Okay, that's that part. Everybody good with that? Okay. Minus 3 times c of a squared. So let's use parentheses here. Minus 3 times c of a squared. This tells me which function I'm using. C. This tells me what I'm plugging in. A squared. So that would be this piece. Okay, everybody see that? And then from here, it's just like doing a little bit of algebra. Okay, let's take it piece by piece. So I gotta take care of like the exponents first. So here I need to do 2 and then 2a minus 1 times 2a minus 1. I'd have to distribute that out first. Here, I don't have anything outside my parentheses here, so I can essentially just kind of drop those parentheses like that. All right, let's just do this part first, and then we'll tackle the green part, okay? All right, so here, that would be 4a squared minus 2a would be minus 4a plus 1. You can add these guys together. Then I could distribute the 2. And combine like terms.
Okay, I have a question.
We're not done.
No, I mean like with the other part.
Yep.
So why would you put negative 3 times that though? Because if the negative 3 were to C, that would be on the other side.
No, because it's not included in the parentheses, and when we write two things next to each other, we assume that's like multiplication going on there.
Oh, okay.
Yep, good question. Okay, now I'll tackle the green part. Where would I start in here? Yep, I gotta do the a squared to the power 3. Power to a power, what would I do? Multiply, that's negative a to the 6th. A to the 6th times negative 1, negative a to the 6th. Then I can distribute the negative 3, so it becomes positive 3a to the 6th plus 6. -6. Good catch. Thank you. Okay, now the only thing I want to do, folks, here is rewrite this like in standard form. So this all would evaluate to 3a to the 6 is my largest power term. Then my next would be 8a squared. Then the -6a. And then the constant last. And that is what b of 2a minus 1 minus 3 times c of a squared. Whoa! You guys, don't worry. There's something like that in your homework you can practice. Like 4, 5, or 20. I don't know.
That's how much.
Okay, questions. Are we good with that? I think it helps, honestly, to be able to like read it out loud and then also kind of do like a little template with the parentheses. All right. I have a little activity for you guys. Kind of. I want you to go through, I have 4 problems here. I gave you 2 things. I gave you an equation and I gave you a graph. Let's look at number 1 together. My equation is x squared. You know that's just our boring old parent function for a parabola shaped, for a quadratic function. And it's a u up because my leading coefficient is a positive 1, right? So this is a degree what? 2. Is 2 an even or odd number?
Even.
So this is an even degree polynomial function. My LC is what? Positive. Okay. I want you to go through and do that. And then when you flip your paper over, I'm going to give you one like this and see if you can guess, based on patterns you see, what degree and what leading coefficient this one would be. Okay.
I think I know that one.
Yeah, so do this quick. I'm going to give you like a minute. Fill this out. I know it's annoying, so you're going to have to flip back and forth. And then based upon your findings here, see if you can guess what this one would be. Honestly, why? Wait, don't say it out loud, actually. Never mind. Think it in your head.
Because it says right there.
Yes, nice job. Oh, that's what 9. Oh, I think this one's 57. That's the next one. Good job.
57.
Okay, number 2, degree, even or odd?
Even.
LC, positive or negative?
Negative.
Here's what a cubic looks like. Degree, even or odd?
Odd.
LC?
Positive.
Odd, negative. Okay. What are some things we notice here? Any patterns? Nick?
If the degree always, like, if it's even, it's going to make the parabola. If it's odd, it's going to make the mean.
Okay, good. I like that. Other patterns. That's more because this one's a degree 2 and this one's a degree 3. Good. Yes.
Negative is opposite of positive.
Negative is the opposite of positive. What do you mean by that?
Like the graph is like flipped.
Okay.
Transformation.
I like that. I like that. If it's a positive, the negative, it just looks like it's flipped upside down because it's reflected over the x-axis. Same with this one. Okay, what else? Notice these arrows I'm drawing in. Another pattern.
That one's going up. Oh, the positive ones go up and the negative ones go down.
Okay, yeah, from like left to right, like the negative one goes down like this and the negative one goes down. Good. Here, the positive one, they're both up and it goes up. I mean, this one's still down, but good. I like that. What's the difference between the even and odd with like the arrows I drew in?
Split in half.
Okay, what do you mean?
Well,
They're not even.
it's split in half, so instead of going hua, it goes hua.
Okay.
They don't go in the same
I think I
direction.
get what you're saying.
They don't go in the same direction.
They don't go in the same direction. Good observation, Connor. That's what I was kind of trying to get you to see. Okay, so this one, and I already kind of showed you, this one is a degree 4, but what do you guys think? Even or odd? Even's the right answer. The reason why is look at the ends. They're both going in the same direction, right? Similar to a parabola. This pattern holds true for all polynomial functions. Do we think the LC would be positive or negative?
Negative.
Why?
Because it's going down.
Going down, exactly. So there's this really cool pattern with polynomial functions. We call it end behavior. End behavior because it's what the ends are doing. And it is solely dependent on if the degree is even or odd and the LC is positive or negative. And this would hold true for like any degree polynomial function ever. So that one I mentioned before of like what I say, like 3027, something like that. It's an odd degree polynomial function. I could predict what the ends of the graph are going to be doing. Okay? So there's a little bit of notation stuff here, but it's not actually too difficult once you understand the notation. So let's start with even. If I have an even degree, and you guys all know what even numbers are, 2, 4, 6, 8, 10, yada yada. If I have an even degree polynomial functions, the ends are going to be going off in the same direction. And whether they're both going up or they're both going down depends on the LC. So if the LC is positive, both ends are going up towards what we call positive infinity. And if you want to sketch in like a parabola, that's what you can compare it to. Because you guys know if we have a happy face parabola, it's u up, both ends are going up. So this end behavior, just like this piece, both ends will go up towards positive infinity for every even degree polynomial function with a positive leading coefficient. Okay? If the leading coefficient is negative, think of a sad face parabola. That just means both ends are going in the same direction because it's even, but they're both going down, just like this one we predicted. Even though it's not a parabola, I can still predict it's an even degree polynomial function because the ends are doing the same thing. Since they're both going down, it's going off to negative infinity, what we call that, because the leading coefficient is negative. Okay, that's even. Odd, they're going off in two different directions. So odd degree polynomial functions would be like 1, 3, 5, 7, 9, 11, 13. Any of those would be odd degree polynomial functions. So actually, a linear function degree degree 1, that's an odd degree polynomial function. And look at the ends. Aren't they both always going off in two different directions? Depending if the slope is positive or their slope is negative, right? So you can compare this one to what you know like about a line. So if the LC is positive, think of like a positive sloping line, this end to the right here is going to be going off to positive infinity. And if you want to dash in a line to compare it with what you know, this end's going off towards negative infinity. Two different directions. I'll explain this notation in a second. And then my last case scenario is if I have an odd degree with a negative leading coefficient, think of a negative sloping line. This end to the left here is going up to positive infinity. I'm going off to negative infinity. Okay, so let's tackle this notation now. This says, what is your graph approaching as x approaches negative infinity? Okay, x we measure on this axis, right? That's my x-axis. Where on this number line do I have negative numbers? Would that be off to the left or to the right? To the left. So it's saying, what is your left end behavior doing? That's what that's saying. Is my graph going up towards positive infinity or down towards negative infinity? Up towards positive infinity. So you say, my graph, f of x, or you can think the y values, because f of x is another way to write y. The y values are going up to positive infinity towards the left. That's what this means, as x approaches negative infinity, the left side of your graph. That's negative infinity for x. All right, so then it says as x approaches positive infinity, that would be the right-hand side. Well, my graph is still going up towards positive infinity. It's going up in both directions. Okay, does that notation make sense? What are your outputs? What is your graph going up to in both directions? So in this case, as x approaches negative infinity, my left end behavior here, it's going down towards negative infinity. You can do negative infinity. And as x approaches positive infinity off to the right here, my end behavior is still negative infinity. Now, because even degree polynomial functions, because their end behavior is always doing the same thing, these two should always match. And whether it's going up to positive infinity or down to negative infinity depends on the LC, the leading coefficient. It doesn't matter if the leading coefficient is a 10 or a 7. It just depends if it's positive or negative. And what you guys know about transformations, that's because of reflections. Okay, so then odd degree polynomial functions. Again, this depends on my LC. So if the LC is positive, as x approaches negative infinity, what does my graph approach, guys? Negative infinity, right? My left side's going down. All right, and as x approaches positive infinity in this case, f of x is approaching positive infinity. I think the easiest way to remember that is just by drawing like a quick sketch. I'll show you an example. All right, then my last one here is very similar. It's just flip-flop. So this one, my left side is approaching positive infinity. And my right side is approaching negative infinity. Okay.
I heard it. I didn't see it, but I heard it.
So I'm going to just give you an equation, and you're going to tell me what the end behavior is by just looking at the equation. So you only need to look at two things. If the degree is even or odd, so what degree is this first one? 4. Is 4 even or odd?
Even.
Is the LC positive or negative?
Negative.
Negative. Doesn't even matter what this number is. You're just looking at this. It's negative. So I do a quick sketch. I'm like, okay, even means they're doing the same thing. Negative means they're both going down. So my graph is approaching negative infinity in both directions. I think drawing a sketch helps. What degree is number 2?
Odd.
Okay, it's 5 even or odd. Is the LC positive or negative? Positive 3. Okay, so odd. What I just do is a quick little positive sloping line. That goes up from left to right. Looks like that. That's what my ends are doing. So as x approaches negative infinity, that's my left one. That's this one. It's going down. And as x approaches positive infinity, it's this one. It's going up. Okay, one more. Degree what to number 3? Odd. It's a degree 3, which is odd. LC? Negative. Okay, so odd, I'm thinking of a line, negative slope, something like that. As x approaches negative infinity, they're talking about the left arrow. That's approaching positive infinity. As x approaches positive infinity, we're talking about the right end behavior. Going down, negative infinity. So again, anytime it's even, those should be the same. Anytime it's odd, it should be one or the other, depending on what the LC is. Okay, any questions on end behavior? All right, let's keep going here. We might not quite finish everything, but that's okay. Other key features of polynomial graphs. When you see the vocab real zeros, do you guys remember what a real zero is like on a graph?
0.
No, not the origin. When I say like a 0 on a graph, like what point am I talking about?
On a line?
What did you say?
That's handy.
On a line?
Okay, what line?
X.
Not y-intercept.
Oh.
X-intercepts.
Yeah.
Yep, these are your x-intercepts. Remember when we did those parabolas? And you solved them by graphing, you're looking for x-intercepts? Okay. So odd degree functions will always have an odd number of real zeros. Even degree functions will always have an even number of real zeros. Or sometimes we can have no real zeros at all. Think of like a parabola. We could have 2 zeros. That's an even number, even. Now, we do have ones like this. But remember when it touches, like those count as 2? Remember that? Because like when you solve this algebraically, you'd get that answer twice. So that still counts as 2 zeros. Or we could have no zeros at all if we have one of those floaters and we get imaginary numbers. Okay, that's what that's saying. Other vocab. Turning points. These are really interesting points in our graph, and this plays into our lesson a little bit tomorrow, too. Turning points, which I often abbreviate as TP, so if you say TP, that means turning points. Let's think of a parabola, something we know. A turning point is where your function or your graph changes from like increasing to decreasing. So if I had a happy face parabola, we don't even need to draw an axis. If I had a happy face parabola, it'd be decreasing, decreasing, decreasing till I get to my vertex, and then it switches to increasing, 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 increasing. We call that a turning point. Specifically, folks, would that be a max or a min? Minimum, remember that? Okay, so these turning points are really just maximum and minimum values. Let's think of a sad face parabola. Increasing, 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 increasing till I reach the vertex. Then it decreases, decreases, decreases. So we call that a turning point. And in that case, when it changes from increasing to decreasing, we have a max. Okay, we'll stop here. We just have to do that one example, but you should be able to get a good start on a lot of the homework tonight, folks, so don't put it off.
How much things are there for you?
Body.
There, I think it's just a book size.
What?
I better check, but I don't want to lie to you.
Right.